I'd like to introduce you to Giselle the Gazelle. Giselle is a very good student of physics. And like most good students of physics, she has a lot of good questions. A few days ago, she asked me, I don't understand this strange relationship between centripetal acceleration, speed, and radius when an object is moving in circular motion. Where does it come from? So I told her, Giselle, you can derive that relationship theoretically, but you can also design an experiment to figure it out by measurement. And that is what she did. The next day she came back and she had a great idea to find that relationship. This is what she came up with. Here is a rotating platform. And as you can see, we can rotate it at various speeds like this. We can go, oh my goodness, Giselle, are you all right? I'm sorry about that. I think I was going too fast. Are you okay? Okay, look, let's put you aside here so you'll be safe. Okay. Sorry. As I was saying, we can rotate it at various speeds. We can make it go very fast and then let it slow down and eventually come to rest. Now here is a force and acceleration sensor. This device can measure centripetal acceleration and speed as a function of time as the object is rotating. And this connects to the Chromebook and we can collect that data. And there's no wires, it connects by Wi-Fi, so there's no wires to get in the way. So I'm going to start rotating, and then Giselle, let's have you press the button on the Chromebook to start collecting the data, okay? Come over here. Okay, I'll start it rotating. Here we go. Okay, Giselle, now you press the button. And now we have our data. So our next step is to analyze that data and find out that relationship. Here's the data that we collected. At the top is acceleration versus time, and at the bottom is speed versus time. And you can see that both are decreasing as time increases. Now, if we want to see how centripetal acceleration depends on speed, we should plot centripetal acceleration versus speed. And this is what we get. It almost looks like a quadratic function. So let's do a quadratic fit to this line. Here's what we get. It's a very good quadratic fit. Y is proportional to x squared here. And x squared, x is a speed, so x squared is speed squared. So this suggests that we should plot acceleration versus speed squared. That's what we did. And we should get a straight line. And that's exactly what we get. Now let's do a fit for this line. We have curtains here because this slide is very important. So there's our fit for this line. It's a very nice fit. R squared is 0.9996. And we can see y equals 6.4945 times x. So y is the acceleration, x is speed squared. So y is proportional. So acceleration is proportional to speed squared. Now what is this coefficient in front of the x? In our experiment, r was 15.5 centimeters, which is 0.155 meters. If we take 1 over r, we get 6.452 meters to the negative 1. Look at that, 6.452 compared to 6.4945.
that is a 0.65% difference. So it looks like that coefficient in front of the x is 1 over r. So now we can write that centripetal acceleration equals v squared over r. That's what you wanted to find out, isn't it, Giselle? Now, let's look at the direction of the acceleration. So here's an object moving in a circle at constant speed. So it starts here and it ends up here. So the initial velocity is vi, v initial, and the final velocity is vf, v final. Acceleration is delta v over delta t, which is v final minus v initial over delta t. Now, if we want to subtract two vectors, what we can do is add the negative of one of the vectors. So instead of subtracting vi, we add negative vi. So to get negative vi, you just reverse the direction of vi, like this. Now let's add the two vectors. So I'm going to move vector negative vi. I'll put the tail of negative vi at the head of v final, like this. And then I form the sum. I go from the tail of v final to the head of negative v initial. And that's what I get. That's delta v. So what we see here is that the acceleration is directed towards the center of the circle. And it's called centripetal acceleration, or AC. Let's look at that close up. There's our v final. We added it to negative v initial, and here's the delta v, directed towards the center of the circle. Now let's see what happens if we increase the magnitude of the velocity. So now I've increased the magnitude by about 3 times. So there's vi, and there's v final. Now we're going to find the acceleration, which is delta v over delta t. So we subtract the two vectors, or add negative vi to vf. To get negative vi, we just reverse the direction of v final. We move it over and find the sum, which is delta v, right here. Again, it is directed towards the center of the circle, and it is larger than delta v for the smaller vectors. Here it is up close. V final, negative v initial. There's our delta v. Going from the tail of v final to the head of negative v initial. We see that it is directed towards the center of the circle, and it is a greater magnitude than what we originally had, which is the black vector here. So AC is delta v over delta t. Now we've seen that when we increase v, we increase delta v. Now when we increase the speed, we're going to decrease the time to go that same distance. This is the distance. It's the same for both speeds. Since it's the same distance and a larger velocity, it's going to do it in a shorter time. So we're going to decrease delta t. The result is that when the speed increases, the centripetal acceleration increases. Was speed constant in our experiment? Giselle, this is a question for you. You are correct. It was not constant. Clearly, it went from a high value and slowed down and came to rest. Remember our plot is speed versus time? It started high and then went to 0 and stayed at 0. This looks like a nice linear function. Let's do a best fit for this linear part, not including the part where it has already reached 0. If we do that fit, we find this. We find a constant rate of change of speed. This rate of change of speed is called the tangential acceleration, and the symbol is AT. And we can find it from the slope of our best fit line. So the tangential acceleration is negative 0.563 meters per second squared. Negative means that it is slowing down. It is directed opposite to the direction of the velocity. Let's look at an object moving in a circle at decreasing speed. And let's see these two accelerations which we have just found. So here's the location of the object. And it's got a velocity v. Now, because it is moving in a circle, it is changing direction. So it has a centripetal acceleration directed towards the center of the circle, AC, as shown here. But it is also changing speed. So it has a tangential acceleration, which is tangent to the circle. And in this case, it is directed opposite to the direction of v because the object is slowing down. This tangential acceleration causes the speed to change. And then there's the net acceleration, a net, which is the vector sum of the centripetal and tangential accelerations. Let's form that vector sum. Let's move the tail of AT to the head of AC. And let's form the summation vector, which is a net.
Giselle has another great idea. You are always coming up with great ideas. She wants to take the force sensor and move it to different radii and repeat the experiment. And then we can see if acceleration is proportional to 1 over r for a fixed value of speed. So let's do that. First, I'll take off this. It's now at 15.5 centimeters. So I'll take that off and move it at first to 22 centimeters. Giselle, I don't want you to fall off again. So I'm going to put you over here for safety, okay? I'll take this off. Move it here to 22 centimeters. Let's just verify that. So there's 22 centimeters. Let's tape it down. Okay, so now I'll start it spinning and then we'll collect the data. No, Giselle, that's not safe. Oh, okay, yeah, we can try that. Okay, so Giselle really wants to go for a spin. She loves this thing. So, but her idea, another great idea, is to tape her down for safety. So I'm all for safety for Giselle. Okay, there you go. Now I will start it spinning and collect the data. Giselle loves this. Here we go. And I'll collect the data now. Now data is being collected.
Here's some of the data which we got in this experiment. These are plots of centripetal acceleration versus speed squared. At the top we have it for r of 7.2 centimeters and at the bottom for r of 22.6 centimeters. In total we looked at 6 different radii. And you can see that these are linear plots, which is what we expected. Acceleration is proportional to speed squared. And these are the two lines that we fit. Now, we want to see how centripetal acceleration depends on radius for a fixed value of speed. So we've decided to choose a speed of 1 meter per second, or speed squared of 1 meter squared per second squared, right here and right here. So we set speed squared to 1 in our best fit line and find out what the acceleration is. So the experiment was done for 6 values of radius from 7.2 centimeters to 22.6 centimeters. Those are the values. And for each radius, we found the acceleration as I described when v equals 1 meters per second. And here's what we found. you can see that as r increases, the acceleration decreases. So to see how acceleration depends on r, let's plot acceleration versus radius. Here's what we get for our 6 points. Let's fit this with a power function. There you go. It's a very nice fit. X to the negative 1.012. So in this thing, y is the acceleration, x is the radius. So it looks like acceleration is proportional to 1 over r. So let's plot acceleration versus 1 over r. Here's what we get. A very nice straight line, which is what we expect. Let's fit the line. There we go. A very good fit. Y equals 1.0223x. So y is the acceleration, x is 1 over r. So y is proportional to 1 over r. What is this coefficient? 1.0223. Remember that v is 1.0 meters per second. So v squared is 1.0 meters squared per second squared. So it looks like this coefficient is equal to v squared. There's only a 2.2% difference between them. So then we can conclude AC equals v squared over r. Here is a summary of what we've learned about acceleration in circular motion. First of all, there is centripetal acceleration. It is directed towards the center of the circle. It causes the direction of the velocity to change, and it is given by this function, AC equals v squared over r, where v is the speed and r is the radius. Tangential acceleration. This is directed tangent to the circle. It causes the speed to change. It is equal to the rate of change of speed. So we can write AT equals the slope of v versus t, which is dv by dt. Thank you very much for staying to the very end of this presentation. Giselle and I appreciate your attention. If you enjoyed this video, please be sure to like and subscribe, and leave a comment in the space below. Thank you.
Wasn't that fun? You had a lot of fun, didn't you? Okay. There you go. You're a good girl. Okay.